Okay, welcome to Thermodynamics. Here we are all again. What a happy, shiny faces we see out there today. Um, I the homework. If you turned in homework yesterday, it's on the back counter. That's where I'll kind of return papers, and that's where they are. Um, what else is there? There's something else that was really important I was going to mention, and I forget what it was. There's a lab coming up indeed. But that's not what I was thinking of, because I was thinking of that too. If you are wondering, there is a stapler we keep in the back of the room there. If it's not on the countertop, it's in the overhead cabinet above. So if you come in with a bunch of papers and you need to staple them, it's there. I don't know. Yeah. So that's that. We just finished up talking chapter 2. And now we're going to start chapter 3. And we're still working up to actually talking about thermo. We're getting some background for that. We're talking about, we've done some calculations now for energy. So let's talk about it a bit. There's macro, meaning big. The big picture would be macroscopic. There's forms of energy with kinetic energy, motion, momentum, kinetic energy, potential energy. It's basically caused by gravity. And it's relative to some datum, not necessarily about absolute elevation. It's about how high is it above the outlet of something that's, or where you're going. There's elastic energy that can be stored. Springs store energy, 1/2 kx squared for a linear spring. And there's nonlinear springs. Virtually all of your cars have nonlinear springs. They're nice and soft. If you have a small motion, you hit a big bump, suddenly they get stiff so that you don't just whack your way all the way down to the stops. But you can store energy in a rubber band, pull on it, and force times distance, and it'll give it that back to you. And then there's the microscopic, molecular scale kind of stuff. The molecular motion, there's chemical bonds, nuclear bonds. And a lot of thermos dealing with them, just the sort of the stuff we call in the molecular motion that we call temperature. It's really kinetic energy is what temperature is all about. I had a problem with this whole concept of sensible energy, and I mean sensible really. I mean, my mother would say, "Be sensible." It's different. It's not like that. If you have sensible energy, that means you can sense the temperature difference. The energy increases and it got hotter. So you can sense how much energy by putting a thermometer in it. That's what sensible is about. As opposed to latent energy, they used to call, back in the way back days when cameras weren't digital and you had film, and the film had a silver halide. The silver, if light hit silver, it would change, chemically change, and then you could develop it. Until you developed it, it had a latent image. You couldn't see it, but it was there. And the latent is the same sort of thing. It's hidden. The latent energy is when you have phase change. If you have a pot of ice water and you put a flame under it, yes, it will absorb energy, but it doesn't change temperature until all the ice is gone. And all that energy is going into phase change. You can't measure it with a thermometer. You might be able to measure how much of the ice has melted, and it's a mass-related thing, but it's not sensible with temperature. So that's, I won't talk about this too much. We'll kind of talk about latent energy. But sensible energy uses our friend C/P constant, or whatever the C is about. And latent energy uses a different thing. It's mass related, whereas the sensible energy is the temperature scales it. Specific heat, C sub P is a specific heat capacity. That's why it's a C, it's a heat capacity. How much heat can something absorb to go up a degree? So it's heat capacity versus the latent energy, the latent heat. They call it latent heat energy, latent heat capacity. And all of that has to do with this molecular motion. Basically what goes on when something becomes a vapor, there's three basic states of matter that we're dealing with. There's solid, and the solid can be a crystal or not, but it's a solid. And then there's, liquid and vapor. Well, when it goes from liquid to vapor, it launches, and it's like in outer space, and it's a lot of space between molecules. Because of their energy, they zing really fast. When they go slow enough, the sort of molecular forces will make them kind of stick together, and the whole thing gets a lot smaller. The difference in volume between liquid and solid is not much because they're already close together. In fact, in the case of water, ice is actually less dense than the water is. And how do we know that? It floats, the ice cubes float, icebergs float. Not much, but it's like a 4% expansion when it goes from, they're going fast enough, they kind of slide past each other. When they lock into form, they actually expand just a little bit, which is different from almost everything, most other things. Most other things, when they solidify, they'll get a little bit smaller, and when they get colder, it's bigger when it's hotter, and it shrinks as it goes, and then it solidifies and it gets tighter. If that happened to water, life wouldn't happen, really. It's one of the weird things about water. We take it all for granted, but if it got a little bit smaller when it got that much colder, it would sink to the bottom. And all of your lakes would be mostly ice with a little bit of water on top. There's no reason for any way to get the heat down into the lower, it would freeze. There'd be no fish. It would be a huge, keeping the ice, it would just be different. So, water is weird stuff. So anyway, there's different ways, I think I've been talking about this, different ways that you can store the energy just with motion, by rotating, by vibrating, how fast the electrons are going, how much they're spinning, so forth. And the internal energy sums up all of that purely about the temperature and how fast molecular motion is. Now, if we take something that's just about temperature and we compress it, we've done, not only does it have, it's due to its temperature, it's spinning and all that, but in working, we added work to it to take it from this to that size. They have numbers for this, and again, this has to do with how fast molecules are going. It will affect how much, like reactions, how fast they happen. So the chemistry guys spend a lot more time on this. We're going to kind of gloss over it and say it's already built into another property of enthalpy that we're going to use a bunch that includes heat and work together. So let's see, what do we got in this slide? Yeah, the actual heat, if you take heat transfer, which is 316, MET314, it's the last third of your book. Energy happens because the room, if the room's 25 degrees and the can's 25 degrees, there's going to be no heat transfer because they have essentially the same energy levels. There's no net heat transfer. The heat energy goes downhill. It goes from a high source to a lower source, just like everything else. Your car isn't going to automatically roll up a hill, and energy doesn't automatically go from a lower temperature to a higher temperature. You can force it to go, just like you can push your car up the hill, but by itself, it wants to go downhill. So it's always going to go from a high temperature to a low. And if there's more temperature difference, that will happen faster. Just like your car goes down the hill faster if the hill's steeper. So heat and work are both energy things, and most of what thermodynamics is about is setting it up so that you can invent something that will convert heat into work, because we have fuels that'll make heat for us, and we have cars or industrial machines or electric generators, what have you, that we need mechanical work to generate useful stuff. So when we have a system, we define the boundary, closed system, there's heat that goes in, there's work that goes in, there's heat that comes out, work that goes out. We're going to look at this boundary and then do first law, conservation of energy, and see if this much heat goes in and no heat comes out, then we would expect, if the system itself isn't getting hotter, we would expect some work to come out. If we put work in, we might expect heat to come out. So work and power, mechanical work is force times distance, joules and newton meter. They also have in terms of foot pounds. There's also a definition, a joule per second is 1 watt. You might have heard of watt in terms of light bulbs. And there's no motion going on in the light bulb, right? But it turns out 1 volt is 1 joule per coulomb. A coulomb is a bucket full of electrons. There's a number. It's not 6 times 10 to the 23rd. It's a different 6.02, I think, times 10 to the 19th. It's a number. And if you take those and try and squeeze them together, and if you have 1 coulomb and you put 1 newton meter worth of work into them, they will be 1 volt higher potential. You're putting potential energy into them. If you then let them leak out at the rate of 1 coulomb per second, which would be an ampere, 1 volt times 1 amp gets you joule per coulomb times a coulomb per second, and the coulombs cancel, you get a joule per second, you get a watt. So 1 volt times 1 amp is 1 watt. It's also a newton meter per second, or 1 newton of force times 1 meter per second. So that's electricity and mechanical stuff. The units are interchangeable, so you can, that's how you can get things to, yeah. So that's where, that's how we could turn 1 kilowatt hour into 3,600 kilojoules worth of energy. A kilowatt was how fast, and you do it for a certain amount of time, and then you get a bucket full of kilojoules. And 1 horsepower is 550 foot-pounds per second. That's the definition for that. And I should also add, in front of your book, 1 horsepower also is 746 watts, almost 3/4 of. If it was 750, it would be 3/4 of a kilowatt. That's what 1 horsepower is. And electrical power, those of you who have had or are going to have 221, Ohm's law, V equals IR, and if you substitute that into your power, is voltage times current. And it gets a little funky with inductance things, like there's volt amps. Yeah, there's your maximum voltage on an alternating current. This is for DC alternating current. Your maximum voltage could happen at a different point in time than your maximum current. There can be a lag. So they talk about volt amps sometimes. Say, what's the maximum amps, maximum volts? The watts might actually be a different number. I won't get into that. But so 100 watts times 100 seconds. 100 watts is a joule per second. Times 100 seconds, we got 100 times 100 is 10,000. And joule per second times seconds, we get joules at the 10 kilojoules. That's essentially what you did with your last lab. Another way you can do work and power, and this is what makes your car go down the road, or your bicycle, same deal. The amount of work you do is the torque times the crank angle, essentially. So on your bicycle, how much work you do is the force times your crank. That causes a torque. The torque causes a rotation. Your wheel's going to turn. The ground's going to go underneath you as far as, you know, how much the angle that your wheel went through, and the amount of force you put on there. That's the work you did. How much power is how fast you turned the rate at which you did that work. So torque times theta, you cause torque by having your foot on the pedal, and if you go 2 pi radians, that would be 1 revolution. That's going to make you go forward a certain distance. How much work did you do? It's probably going to correlate to how much, force times distance your bicycle went. And the basic thing for the basic formula for power, mechanical power, is torque times omega, which would be radians per second. Radian is the only unit I can think of that you probably don't have to worry about canceling. It's like a unitless unit. Revolutions, if you do like, foot-pounds times RPM, revolutions per minute, and you do all the units, revolutions doesn't wash. You have to turn revolutions into 2 pi radians, and then your numbers will come out. Revolutions has a meaning, and you basically have to turn it into radians, and then it disappears. And really, it doesn't totally disappear because a radian is a radius, and so if you have a foot-pound, it's really foot per radian, or somewhere in there. There's actually a radian, and it's not worth trying to follow that. So just assume if you get things into radians, you don't have to worry about canceling out the radian unit. If you have revolutions, you better turn it into radians. And that's here 2 pi. That's 2 pi radians per rev, and then they got n dot is RPM. That would be revolutions per minute. But with this 2 pi on there, you turn the revolutions into radians, and now you got per minute, and then anyway, that's that. Fluid power, you get work for a fluid. Force times distance is equivalent to pressure times volume, if you think about it. Pressure is force over unit area times volume. Volume is area cubed, and the area squared on the pressure cancels 2 of those, and you come back to force times distance. And if you think about it, you've got the piston, like we did in the example. If it's this much area, you have pressure times volume. Well, the pressure is going to cause a force over that area of the piston, and the volume in there is going to cause the piston to move a distance. So pressure times volume. But what if you want power? How fast can you make that go? So hydropower is not about a force times distance and a pressure times a volume. You've got a volume flow rate, cubic meters per second of water going through the turbines. So you need a volume flow rate. That's divided by time. Where's the time come from? Cubic meters per second instead of cubic meters. And that's how power becomes the speed at which the work gets done. So, first law, energy balance is really what we do. We are accountants for energy, not for money, but for energy. And how do we account for it? With our calculations. And, for most problems, like yesterday in the 411 class, I got up to an example on a nozzle, and I frankly was staring at it and say, how in the heck does this work? And then it was like up to sort of freezing. How am I going to solve this problem in front of all these people? And then I remembered, just go back to the basics. Conservation of mass, conservation of energy. How am I going to do those? And those two tools usually unlock a lot of problems. So, first law says what energy you start with is the same energy you have when you're done. You might have taken heat and converted it into work. You might have heat left over. What didn't get converted into work is probably exhaust. You might have potential energy due to hydropower, due to a pressure. By the way, if you think about it, what is pressure? Pressure is essentially energy per unit volume. If you have more, it's potential energy per unit volume. I'll have to go through the numbers on that, but well, if you think about it, a Newton meter is energy. If you divide it by volume, meters cubed, one of those meters cancels, you get newtons per square meter. That's pressure. So energy per unit volume is pressure is potential energy, and the more volume you have at some pressure, the more potential energy you have. You don't. That's probably not in your book. It's pressure is really another potential energy. So that was a little off topic. Energy balance. So we're keeping track of things. If energy comes in and energy goes out and we do some work, then if we did more work and put in more energy than is coming out, that means the change in energy in this one, for example, we heated it up with 15 kilojoules, we stirred it up with 6 kilojoules, and 3 kilojoules leaked out through the insulation. We can predict that the internal energy increased by the difference between what went in and what came out. If we knew how much mass that was and what the material was with the CCP, with this much energy, we could predict how much the temperature went up inside. But it's all just the temperature is telling us how much energy there is there. So that's supposed to be a delta. I gotta go through my slides. It seems like every 2 or 3 years they change PowerPoint to make it more user-friendly, and at which point, all my symbols, they pull out the format I was using, and then suddenly all the symbols go to hell. So, I don't know.
The one on Canvas is okay.
Yeah, that's because it works just fine on my computer at home. It works fine on the one in the office, and then you come up with a brand new, shiny new computer, and God. Yeah, I had no clue that I'm reminding myself that I got to go through all my slides. Yeah. So, imagine this. You got a nice insulated room. It's a really hot day, and you're thinking to yourself, my refrigerator is so nice and cool, I'll just open the door and cool down the room. Is that a good idea? Why is that not a good idea?
Because your fridge is going to become the temperature of the room.
Yeah, and will the room get any cooler?
Probably barely a little bit.
If it's mixed nicely, if you happen to be the guy that got the chair right next to the refrigerator, you'll probably be cooler. But what happened on the back of the refrigerator? Heat. Yeah, what the refrigerator does, it takes energy from one box and puts it in another box, and it does it without perfect efficiency. It turns out it's actually pretty efficient. The amount of energy you put into it, it'll magnify that cold flow. We'll get to that. But net effect is this room is completely sealed. It's insulated. There's no heat getting out. There's no heat getting in. But there's a plug here. So what do we know if we've got a 100 watt power consumption. Are we generating 100 watts worth of heat energy? It's doing a bunch of, it's taking like 300 watts of cooling from the inside of the refrigerator and taking to the back, and out comes 400 watts or worth of heat. So right in front of the refrigerator it'll be cool, and everywhere else the room's going to get hotter. Same thing, this one, it actually does feel good to be in front of a fan. It increases the evaporative cooling, it increases convective cooling, it increases the heat rate at which you lose from you. As long as the room is cooler than you are, that fan will blow the heat off of you. But what's happening to this room? If same thing, it's a hot day and you think, man, it feels good when the fan blows over me, but so I'm going to leave the fan on all day and close all the windows to cool down the room.
It's just gonna be blowing the hot air around, you'll have circulation, but eventually it'll just level out again.
Again, it's completely sealed. All that's coming in is this, nothing's going out, and we've got 100 watts coming in through basically it's like leaving a 100-watt light bulb on, 100 watts is what it is. Would leaving a 100-watt light bulb cool down the room? No, it doesn't matter if the 100 watts goes through a light bulb or a fan or a refrigerator, it's going to heat up the room. So that's first law. Draw a box around it. It's insulated, no heat going in or out. We've got power coming in. 100 watts times 10 hours, you can figure out how many kilojoules that is. And then if you know the mass of air in the room and maybe the mass of whatever's heating up, you could come up with how much temperature it's going to rise. It might be insignificant, but it's going to be a net rise. So that's an example of our first law. With thermodynamics, we're really going to focus on this sort of thing. There might be work going in and out. There's a mass flow coming in. The mass is carrying. This would be your turbine, for example, the steam turbine. We have steam coming in at some mass flow rate with carrying a certain amount of energy. We're not going to talk about internal energy. We're going to use that term that includes internal energy that we call enthalpy. And that brings in a certain amount of energy to this box. And on the way out, the mass is carrying energy with it when it goes. But it's going to be carrying less energy. And, if it's a turbine, then they're going to get work out of the system, and we're going to get energy out of the system. Energy that's carried with the mass. So we watch our mass flow has to, keep track of that. It's possible that more mass comes in than leaves. If that's the case, this is like a balloon that's expanding, more mass inside this. But in a steady state, the same amount comes in as goes out. The work comes out. And there might be some issues with insulation such that maybe it's hotter than the surroundings and some heat comes out. But we can track all of that. Likewise, for refrigeration, this might come in and maybe this comes in with a certain amount of energy, and now we put work into the compressor. And what comes out is at higher pressure, higher temperature, and that goes to the back of the refrigerator to cool down. But depends if are we drawing a box around the entire refrigerator or just around the compressor, the steam plant. We can define what it is that our system is. But that's what the first law will be. We'll be looking at work and heat. How does it come in? How does it go out? And we are accountants for that. The efficiency of a system. We can talk in terms of efficiency of a system, or we can talk in efficiency of an individual thing. The turbine, the compressor. But what I like is this is always true. What is efficiency? What is it that you want? What useful thing is being done? Divide by what is it? How much input? This is the output. That's what you want, hopefully. What it costs you to get that output. Or you can say desired output over required input. I think that's what your book calls it. or what was the energy that was converted that you wanted, the work that was done relative to the fuel that you put into it, energy supplied. And this is important. The efficiencies don't add up, they don't average, they are a chain. And for each process, for a power plant, there might be a whole bunch of different things that go on. There's an efficiency of the combustion. Maybe you have a certain amount of fuel energy that they tell you you've got so many BTUs per ton of coal, and you've got X many tons of coal, so how much electricity you're going to get out of it. Well, first of all, you have to burn the coal, and the boiler itself may have, how much energy are you getting out of the coal into the steam. And then the turbine itself, it converts the steam into shaft power with some efficiency. It's not 100, you don't get all of your energy back. And then the generator itself, it takes the shaft power, but it has, bearings that have drag on them and whatnot. The generator itself has an inefficiency. Then this chain, if this is 50% and that's 50% and that's 50%, you don't get 150% of your energy. You get 50 times 50 is 25 times 50, you get 12%. 0.5 times 0.5, half of half of half. So like 12.5% or something like that. The efficiencies chain. As it turns out, electric efficiencies are pretty good. Thermal efficiencies, like the very best power plants, maybe 42% efficient for a super huge one with a whole bunch of complications. That's like really, really good for the whole power plant. Which you think all the things going on, that's a whole chain of efficiencies, and altogether they get you to 42%. They all have to be like 85, 90% efficient processes to do that. Now there's the effectiveness, which isn't exactly the same as efficiency, but because you're not comparing the same units necessarily. Yeah.
So on that last one, you said you had to add all the efficiencies together, or time together.
Yeah, they multiply.
Could you figure out how much you have coming in, right? How much BTU the coal has, and convert that to how much electrical power you should make, and then divide that by how much you actually got, and would that give you the same number?
Yep. And that's where, if we get to the example today, we're going to do that for a hydro plant. We know how much came out, we know how much went in, we can take the whole system, and then if you know the one part, you can find what the other part is and start teasing it apart. Yeah, definitely, you can do the overall. You don't have to do each individual thing. So we're not, effectiveness isn't the same as efficiency, but it's almost. Why is that? You want to cook a casserole, food. It may not be a casserole. Anyone cook casseroles? A few people cook casserole. My mother used to cook a bunch of casseroles, basically one pot thing, and you throw it, and it's, yeah. In Lake Wobegon, they call it a hot dish, which is really non-specific. But anyway, if you're going to cook a pot full of stuff, if it's something and you put it in the oven, how effective is the oven? It's got this area this big, it's heating and it's losing heat there, and you put your thing in the oven, and it's just sort of hot air. There's maybe an electric burner on the bottom, and it heats up air, and air kind of comes up, and eventually enough air passes by the pot that it comes up to temperature. But it takes an hour to come up to temperature and cook it, and use kilowatt hours. Now, you use that much kilowatt hours, you don't necessarily have a number for how many kilowatt hours you want to cook your food, so that's why we can't call it an efficiency, but we can compare. And maybe in the electric oven at 325, it takes that much energy to get the job done. You do a convection oven, what's the difference? Same oven, you put a fan in the back of it, and this is used a lot industrial and commercial kitchens. the temperature doesn't have to be as high, it goes faster. How does that work? Instead of the air just being natural convection, it's swirling around and it gets more hot air to it, and so it's more effective. And it happens, not only happens faster, but because it happens faster, you use less energy. There's actually more, you're probably putting the same power into the oven almost, but there's a little bit of fan power in the back that's going on. But net effect is you save some money, it's significant reduction. If you put it into a gas oven, same deal as this one, but the cost of the energy, you're using natural gas. You might actually be using more, if you could turn a therm is 100,000 BTU, is how they sell. They don't sell natural gas by the pound or whatever, they sell them by therms, which is an equivalent of, it's actually 100,000 or a million or something. There's a number of it. That might actually be bigger than this number, but the natural gas, the thing about that is to make the electricity for this, you might have to use natural gas to do it. And when you're done, the electric plant was only 30% efficient. And if that's the case, and the plant plus all the distribution, so you could waste more energy and burn the natural gas directly at the source, and you'd be, the environment would be a happier place because you ended up burning less gas to put it in your oven than you did burning at the power plant, shipping the electricity and then turning electricity into heat. Because the electricity you get is only something like a third of the energy that they started with the fuel. So if you just burn the fuel directly, you save, and less than half the cost with the natural gas. But then this is based on certain costs for things, but so what if you did a frying pan? You just put the pan on the stove. Now it pans directly on the burner. Because it's on the burner, you get more direct. You're not heating up the whole oven and losing heat that way. Maybe in the frying pan, it still takes you an hour, but it takes you less energy because you only have one burner going, and you're saving some money. Put it in a toaster oven, a smaller oven, smaller space. You're not losing so much energy to things other than what you're cooking. Comes down even more. Slow cooker. That's crock pot. You put it in there, you leave it all day, but it's at a really low power consumption, and it's fairly well insulated. It saves you a little bit more money. I like to put a towel on top of my, the slow cooker. When I'm cooking something, put a towel on top to insulate it, and then turn it down one tick, and it gets just as hot, if not hotter, because the glass top doesn't lose energy as fast. And on a microwave is an interesting thing. It might only take 15 minutes to heat it up because the food itself is the heating element. And it takes less power, and but some things just don't come out the same. Like, everything coming out of the microwave sort of comes out like it was steamed.
Leftovers.
Yeah, it's good for leftovers. You don't want to cook your steak in a microwave, right? Just microwave raw meat and then eat it. Does that sound good?
Microwave bacon, it's just like biting jerky.
Yeah, there you have it. I was going to say bacon actually works pretty good for cooking it, but anyway. I don't eat bacon just because that, in general, because of the salt thing.
I've eaten so much bacon, technically, if doctors are right, that it takes 5 minutes off your life. I should have died in 1776.
Yeah, that's saying something.
My grandma was 1800s.
Couple more minutes to get through a few more slides here. What if we talk about, it's another word, like efficiency, efficacy. Doesn't mean efficacy. Why couldn't we call this efficiency? How effective was it at getting the job done? But the job isn't energy. I mean, we're cooking food, but we don't necessarily care, how many kilowatts went into the food. We just want it to be done. So that's how effective was it. Efficacy, another word, we won't be using those words. We'll be all talking about efficiency here, but just to kind of scale things, what is the output? Lumens. What is the input? Watts. Because they aren't the same unit, it's not efficiency. But how effective is it? What is the efficacy? Effectiveness works for me too on this, but lumens is not a power output so much. It's how much light is there. A 60-watt light bulb doesn't put out watts. The 60-watt light bulb puts out light. And how do you measure light? You measure with how well illuminated it is. The root of that word is lumen. And so they used to talk about candle power. Candle power is one candle at 1 foot. How bright is it? And they turned that into lumens. Numbers of lumens. I don't know how it compares, but a candle is 0.2 lumens per watt. You can actually say how many watts. If a candle is burning, you know how much fuel it, for a period of time, it burns this much wax. It made a flame that was this big for that amount of time. How fast is it burning the fuel, and what is it? You can come up with a watt for a candle because it's burning something. Incandescent light. That's your standard light bulb, one you screw in that you can't hardly buy anymore. Gets from 6 to 20 lumens per watt. Take a halogen light bulb, which these are still filament. They get higher, 16 to 25, mostly because halogen has a gas in there that can cool the element a little bit, so it doesn't turn itself into a vapor or liquid or something. And it cools it a little. It has some cooling, so you can actually put more power through it. You can get to a higher temperature, and it doesn't burn itself out. And at that higher temperature, it's more effective at making lumens per watt. Higher temperature gets it more into the zone where our eyes register light. Fluorescent is a different, these are all about a filament that glows to some temperature and gets hot. Fluorescent, actually, it's electrons hitting something that fluoresces. It's like glow in the dark.
I was gonna say,
It's
isn't
a
it like
different-
gas in it that when you hit with an electrical charge glows?
Yeah, so I don't know, it's the gas itself that the electricity goes through the gas because it's conductive, and it generates sort of electrons that hit the surface, and it's really the surface of the glass that has a fluorescent stuff on it. It's related to the gas, but it just, whatever you put, it used to be the old TV screens that were cathode gray, the back in the day TV screens. There was an electron that would come and it would hit a dot, and that dot would light up, and it was a phosphor thing that lights up. So that's how they work, and they're a lot more. If you compare a good incandescent to a fluorescent, it's 3 times as much light for the power. So a 60-watt light bulb, you can get the same amount of power out of a 20-watt fluorescent. And then in a compact fluorescent, there's this little ones. So they'll get the same amount of light, typically a 15-watt bulb, and they sell these as a 60-watt, we'll say 60-watt equivalent. Save a bunch of energy. The watts are the electricity. People are used to buying light bulbs according to watts. So in selling them, they're going to put all this stuff on there that's kind of confusing. It's actually putting out the same number of lumens. Lumens are how bright it is, using a quarter of the electricity. Which is why they've all but outlawed these. You go in the store, you can't buy a standard. You definitely can't buy a 100-watt. They have truly outlawed 100-watt bulbs, which is sad for my wife because she likes 100-watt bulbs in all her light bulbs. But and the fluorescents have a different, especially the cheap ones have a different spectrum. The colors look different because it's not the same spectrum that these are actually have sort of a warm red. That the temperature isn't the sun temperature. So what you get out of these is kind of a reddish color. These, it depends on the fluorescent, what they use for the fluorescent coating you can get different shades. They'll talk about cool white, warm white. Warm white means more red, cool white means more blue. And then you get the high intensity ones, mercury vapor, sodium lights. These are your street lights. They're much more efficient. Mercury vapors, I think, come out really blue. If you're someplace with one of those and you're wearing blue jeans, they look black or some weird color. They don't look right. Sodium tends to come out sort of orange. If you come down I-82 and look at night at Ellensburg, it looks like a whole bunch of sort of orange-red lights. Those are all the sodium vapor sodium lights. And I also looked at LEDs. They didn't have that in your book. LEDs, they measure lumens and watts. They're somewhere around 45, 65 lumens per watt. So they're kind of comparable to your fluorescent in efficiency, but they're useful for a lot of things. So I guess that's where we call it today.